let's move on to the next one. We are working under this umbrella or under this framework of pre-training, fine-tuning, pre-training, fine-tuning. You have pre-training data set, you have fine-tuning data set. But this looks a little bit Boolean. You pre-train, you fine-tune. But there is actually a spectrum of data set from pre-training up until your final task. And there is going to be a spectrum of domains that are defined around a particular task. For instance, you can look at Amazon reviews for a specific product, all of Amazon reviews, all reviews on the internet, and all of the web, which was something like Common Crawl. And what we were doing so far was doing pre-training on the web and fine-tuning. Suddenly go there and fine-tune. If your final objective is to increase the performance of your machine learning algorithm on the final task, we know that there is going to be limited data for it, but at the same time, there are a lot of unlabeled but related data to that task. The web is one of them, but there are multiple other data sets in between at different granularities. The idea is don't stop pre-training. Pre-train on the web, pre-train on your target domain, maybe all of the reviews on the web, then pre-train on all of Amazon reviews, then pre-train on your actual task, and then do your classification, which is sentiment analysis. That's the idea here. And this is actually useful. What are the type of data sets that you can have? You can have Roberta, which is a big model, and it is trained on some data sets extending Wikipedia pages. But then you have some domain-specific data sets, like biomed. It's for biomedical, CS, computer science, news type of articles or reviews for Amazon reviews. So you have different domains. And what you're going to have, this is a paradigm. This is a way of thinking now. You're not going to introduce any new architecture, any new laws. This is about defining a paradigm of pre-training, fine-tuning at more levels of granularities. And the idea is that start with Roberta, it is trained on the web, and then that was domain adaptive pre-training, and then you can do task adaptive, which you have data sets that are related to that particular task. So you start with Roberta, it is trained on the web, then you have a large corpus of unlabeled domain-related data. You continue pre-training Roberta on that, which is you basically mask some of your input, and then you ask what was the word that you masked. But then it's specializing, it's picking up the specific type of language that people in the biomedical field use all the time. So you're adapting it. Then you have your task specific, and that's going to be called tapped. There is dapped, there is tapped. And then the way that you're going to be testing it, you're going to have 8 classification tasks. These are the little tasks here, the darkest ellipse over there. In the biomedical field, you have ChemProt, RCT. For CS, you have ACL, the other one, news, etc. For reviews, you have IMDb, helpfulness. You start with Roberta, and that's going to be your performance. And what are you doing here? You pick Roberta, which is trained on this domain, and then you fine-tune it immediately on the task data. If you do DAPT, your performance is going to increase. If you do TAPT, it's going to increase, but it's going to increase a little bit. But if you first do DAPT and then do TAPT, your performance is going to be the best. And that's the message. Don't stop pre-training. Keep pre-training. So I explained this orange half of the ellipse, this blue area, this dark area for your task-specific data. There is going to be some data set here. What is that? How do you collect it? This data is going to be a subset of your target domain data. The way that you're going to collect that is you're going to featureize that text using a simple featureizer. So don't panic here. It's just a bag of word featureizer here. So you have biomedical sentences, you have ChemProt, and then you want to create a neighborhood. You want to increase the size of ChemProt using biomedical sentences data. You take those sentences, you vectorize them using Vampire, and then now that you are vectorized, you can measure the distance between two vectors. Measuring the distance between two sentences is hard. Measuring the distance between two vectors is simple. Now that you know the distance, we can look at the k nearest neighbors of the chemprod data. And depending on the k, you have different sizes for this gray region. So you're gonna start with a model trained on the orange domain, which is the entire web. You go to the target domain, keep pre-training. You pick a subset of that data using this strategy. You keep pre-training, and then finally you still pre-train on the task. And then one final step, you nail it. You say, now my data is labeled. And then you do your downstream task. And that's the way that you're increasing the performance. I think it's a good time for me to stop. For those of you who have questions, I'll be around.
When you talk about a network biasing towards like a mask token, what does that actually look like? What does that bias actually mean?
So that bias is going to translate into a lower performance on the downstream task.
Okay, so it's just adapting towards translating that token super well. So when that token's not there, it doesn't do as well.
Yeah, exactly. So think of it this way. Let's say you want to do classification, but then your classes are imbalanced. You keep seeing one of the classes all the time, or most of the time, compared to the other classes. And that way you're not going to learn what is happening in other classes. It's the same thing here. It's a little bit more nuanced. You're not going to feel it immediately. You're going to notice it through these numbers. But intuitively speaking, that makes sense. There is going to be bias towards that token that keeps showing up all the time.
Okay. Makes sense. Could you maybe go back, I think, one slide? Yeah. So the causal with prefix, is that which objective functions does that correspond to? Like
this causal with prefix is actually the masking strategy that you use in this model.
Okay, so all the masking strategies are completely indifferent of the
objective, yes.
Okay.
So this is just to give you the architecture. Once you know the architecture, you look at your objective function.
So that causal with prefix would be something like every index would see exploring the limits, but then once you above that, it's completely causal.
Exactly.
Okay.
So it's going to pay attention to every single entry on the input, but then it's not allowed to pay attention to the past when it comes to the output.
Would that have like negative impacts if you're doing something like translation?
Not really. Actually, translation, you can put it in the same architecture. I guess I misspoke a little bit. I'm not sure. When it comes to the output, you are not allowed to look into the future. You're always allowed to look into the past.
Okay. What?
So let's say you are trying to, so far, you translated up until the first word in your translation, and then you want to output the next word in the translation. You are not allowed to look at Y2 because that's going to be cheating.
Okay. That makes sense to me. What happens if you end up training with like an Oracle connection where it can see the future? Will it just not learn very good?
No, it's going to learn. It's going to learn the trivial thing. It's going to learn to copy and paste from the future.
Okay.
If you give it the answer, it's going to create a shortcut from the future to the output.
Okay.
So, and remember, there is going to be residual connections everywhere. So it's going to forget about those non-linearities altogether. It's just going to copy and paste.
Okay. And with all of these, it seems like it's kind of acceptable to look in the future of the input, but as long as you're not looking into the future of the output, because then that'll just be copy and paste. But
yeah, the output is the answer.
Right.
You're looking for "das is good." You are not allowed to look at that.
Which is why the encoder decoder still works, because you can.
Yeah, this one works, and this one also works.
Right. Okay. Thank you.
Yeah, sure.
That's all.
Okay, perfect.